Can you hear me? Hello?
Yes, but
Yes?
barely. So I think your volume's like really low.
Barely. I will try to make my mic louder. Is it better now?
Yes, it's
Yes.
inching towards better. If you could increase that more, that'd be great.
Let's do a bit more. How's it now?
Louder would be better.
Even louder. Let's do it.
Yes.
Like
Okay.
this?
Yes, that works. Great. Thanks.
Okay. I mean, better to get it right now than if you cannot understand me. Okay, and you can see the screen, right?
Yes.
Perfect. Okay, let's do this. Okay. Hi, and thanks for everybody for joining us here at the AI for Content Creation workshop. My name is Manuel Jan, and I'm presenting a joint work with Robin Rombach and Björn Ommer. As you might have seen yesterday, my colleagues Patrick, Robin, and Björn presented a method for high-resolution image generation with transformers here on CVPR that they call VQGAN. And I'm going to show you in this talk how to utilize the VQGAN method for the generation of high-resolution complex scene images. So let's get into this. As mentioned before, the goal of this work is to develop a method that allows to synthesize scene images. And for the purpose of our work, we define scene images as pictures that contain several objects with some sort of natural interaction with each other. These objects include humans and animals and non-living objects. And we will train models on scene data sets such as COCO, Visual Genome, and OpenImages. Please stay in this talk if you want to see how we solve this problem by combining the best of two worlds, CNNs and transformers, and adversarial training and likelihood learning. But before we show our approach, we would like to raise the question of what actually makes up a realistic scene image. We argue that a realistic scene image gets two things right. First, the local structure. In our case, this includes rendering realistic textures for the giraffe's fur, the grass on the ground, etc. Second, there's a lot of global structure in this image that we need to get right. This includes things like perspective and that distant parts of objects are consistent. We need a consistent weather situation and image illumination, and the depicted objects need to realistically interact with each other. And all of these things can only be solved globally, and they tend to scale quadratically, but we show how to mitigate that. In our approach, both the local and the global structure are modeled by an expert in this field. For years, convolutional neural networks have been used successfully for modeling local image features. We combine them with adversarial training to get the VQGAN method, which I will explain in a moment. However, they do lack an understanding of global relations. Self-attention, on the other hand, has been used efficiently to model global structure, and thus we use an autoregressive transformer. Transformers, however, scale quadratically and cannot be efficiently used in pixel space. But we show how, when combining the two, you get the best of both worlds. Before we proceed, I'd like to point out that there are different kinds of image annotations that I use to guide the synthesis process. We in this work use coarse bounding box layouts that provide class label and bounding box coordinates for every object in this image. Note that this is somewhat different to approaches like SPADE that need or use class information for every single pixel of the image. Also, we go directly from coarse layouts to images, where the other approaches use potentially complicated intermediate steps. Let's give you a high-level overview of our method, which consists of two stages. The first stage is, in essence, a convolutional autoencoder, so a network that is trained for image reconstruction via a bottleneck. A special feature of this autoencoder is its discrete latent space that uses only integers. Once we have established such a compact discrete representation of our images, we can model the discrete space probabilistically with a GPT-style transformer. When combining with conditional information about the scene composition, we can guide the sampling process. First, let's deep dive into the VQGAN, then later, let's take a look at the transformer. The VQGAN model is an extension of the VQGAE, which stands for Vector Quantized Variation Autoencoder. Input images pass through downsampling and convolutional layers in the encoder and reach a latent space Z hat. The following quantization step assigns to every spatial position in Z hat the closest vector of a collection of codebook vectors, which are also learned. As a result, we can describe image content just with an array of indices of the codebook vectors. And we typically use 16 times 16 tokens to represent a 256 pixel image. When passing Z through the decoder, we can reconstruct the original image. But until here, we've described the standard discrete autoencoder that tends to produce blurry output, unless when working with a really large bottleneck. But we replace pixel width with perceptual reconstruction loss and add an adversarial training scheme. This is the secret sauce to getting strong compression while retaining image content and object textures. The adversarial training results in extra image crispness. Now, if you've seen the talk of my colleagues, you might be already aware of the advantages of perceptual loss and adversarial training in this context. For example, compare these two reconstructions of the input image on the left. On the right side, we have a standard discrete autoencoder, here represented by the Dolly model. You'll notice that it has a latent space that is 4 times larger than our VQGAN method. Nevertheless, the output is somewhat blurry. Our method, on the other hand, produces sharp textures. The squirrel's fur in the reconstruction might not be pixel-wise identical with the one in the original. However, because of the perceptual loss, fur in the original is reconstructed to fur. Now, let us look at a particularly challenging problem, the reconstruction of faces. Note that this is difficult because in this dataset, faces are not aligned and are only one of many things that need to be learned. Faces are full of details that are difficult to retain in a bottleneck model, and the human perception is very sensitive towards irregularities, as you might experience right now while looking at these images. The standard VAE solution gives a blurred, somewhat smudgy version of the original face, which, however, to our human perception might seem a good solution. Our solution seems to come with more irregularities, but keep in mind that we only use a quarter of the latent space and that when zooming in, the difference becomes more obvious. Beard texture in the original becomes beard texture in our reconstruction. However, the standard VAE just gives a blurred version of the beard in that case. By now, we've seen that we can compress images into a very compact space, for example, just 16 times 16 tokens. We will now show how this space can be probabilistically modeled. We simply pass the image through the VQGAN encoder, unroll the 16 times 16 array to a 1D sequence, and train the transformer with maximum likelihood on next token prediction. So we've abstracted the pixel space, and now our transformer scales. Additionally, we pass layout information, but I will come to that in a second. We first want to show you how to sample images. For a given layout, we encode it and pass it into the transformer that predicts 1D sequence of tokens. We reshape this sequence into an array, pass it through the decoder, and obtain our samples. Now let's also understand how we encode bounding box information in the alphabet of transformer tokens. We encode each object in the image by a triple of numbers, the class label, in the top left and bottom right corner position of the bounding box. We are able to represent bounding box corner positions in just one number by imposing a virtual grid on our image and numbering the grid intersections in a row major fashion. Now, after this detailed view on the method, let's take a look on the results for image synthesis and further possibilities that the model offers. We show here some 512 pixel samples of our models trained on open images or COCO respectively. Keep in mind that all our samples are generated with a layout like the ones depicted in the left image. Notice the visual quality and great object interaction. For example, for a layout where there's a book close to a person, the generated image will feature a person reading a book. When measuring the visual quality of our images with the FID score, we are able to outperform current state-of-the-art architectures by between 19 and 53%. The autoregressive approach further allows us to do image completion. Given, for example, the upper half of a famous image, like this depiction of the Star Wars Death Star, we can reimagine the lower half. By passing layout information, we can now modify the original images to our desires, like adding cars and a human spectator, or imagine the Death Star in the background of a scenery of skyscrapers of a city. And notice here how the upper half image style influences the completion of the lower half. Now, working with the Open Images dataset was especially nice since it contains 11 times more images than the COCO dataset, which is beneficial for the transformer training. But further, it includes several additional flags like the isDepiction attribute, which tells you whether we actually see the named object or just a depiction of it. And that's when we figured out that our model could creatively draw in Paint because all of these are samples from our model for 2 different layouts. And we also wanted to see what happens when we switch a certain scene layout from depiction to real image and vice versa, which is what you see on this slide. A layout of a depicted woman can result in a drawing, or while without depiction, we get photorealistic optic. Similar holds for the photorealistic butterfly that is quite artistically painted by our model. And finally, sampling depicted cars seem to give us car advertisements, but the photorealistic samples look also quite like from an ad. So while I draw a conclusion of our work, you may admire how our model reimagined this famous picture of Notre Dame on the beach. So we added boats and surfers, and suddenly a famous building changes scenery. So in summary, we presented a method for scene image generation that combines CNNs with transformer models and adversarial training with likelihood learning. We generate scene images for coarse bounding box layouts and are able to beat current state-of-the-art FID scores by between 19 and 53%. For further details, please check out our extended abstract. Thank you very much for your attention. I'm happy to have your question, and we hope to see you also in the poster session.
Cool. Thanks for that great talk, Manuel. If there are questions, please feel free to post them in the chat. Maybe I'll start it with one quick one. I mean, what kind of situations does this, I mean, these results look fantastic, and I'm curious, what kind of situations does this model struggle with? Like, what are the limitations?
Okay, I mean, so I think you've seen some, especially I would say like the creation of humans is kind of difficult. I think you've seen the imperfections when I go back to this one here. Okay, this is far from perfect. On the other hand, the question is always how much of that is like our subjective perception that we just, our mind just jumps to these faces that seem imperfect. On the other hand, you can also see that here sometimes we do get some imperfections, that the car line starts here, but then suddenly it changes like there. And this is also so for generating these samples here, the 512 type 512, we used like a sliding window approach, which actually means that we don't have global interaction all over the place, but just relatively in a 256 window. And this can, for example, happen. Also, I think we've seen images where you have a city and there's a sunset in the left, and then you move over to the right, and then the model maybe cannot see that there was already a sunset on the left and draws another one, for example. Things like this could happen.
Long range interactions. Cool. Thank you. There was one other question in the chat. What's the inference time of the second stage for the 16 by 16 sequence?
Okay, so we were using A100, and I think more or less roughly we are in the area of seconds. I can't right now tell you if it's a fifth of a second or if it's 2 seconds, more or less like this.
Cool. Awesome. Thanks so much, Manuel. I think we can now move on to the next talk. in this session, which is texture generation with neural cellular automata. This is a paper by Alexander Modvintsev, Eivin Nicholson, and Ettore Randazzo. And I think Alexander is here to give the talk. All right, thanks. Take it away, Alexander.
Hello, can you hear me?
Yes.
Yes, okay. I'd like to talk about neural cell automata, differential self-organization in general, and specific example that's represented by the paper that we call self-organizing textures. And there are actually two versions of this paper. One is that was submitted to the workshop, and there is another that is a distilled version that contains this interactive demo where readers can play, interact with those models, zoom in, try to see how models work, say if we replace the grid that the model was trained on with hexagonal. So I am going to post the link to this paper to the chat so that well, interested readers can also see the interactive version of the paper. And also there is like artistic reinterpretation of this concept that I called hexels, which is well, like an artwork where I tried to visualize the relationship between cells existing in a small scale and their collective behavior that results in the formation of these patterns. And now I'd like to continue my talk with this video that I recorded like last year that is going to talk about what's differentiable self-organization and what's neural cell automata is all about. So I've posted the link to a chat, so feel free to like mute me somehow and watch it on YouTube. Neural cell automata model and its applications to designing self-organizing systems for solving a variety of tasks. Generally speaking, differentiable self-organizing system consists of a neural controller that is shared by a population of agents interacting on a simulated environment during a limited time span. The whole system is evaluated against an objective function that measures the proximity of the current behavior to the desired. End-to-end differentiability allows propagation of the objective gradient to the controller, steering the system behavior towards the target specification. Neural CA operates on a uniform grid. The state of each cell is represented by a number of real values, 3 of which are visible as RGB color channels. Cells iteratively update their state using the information collected from their 3x3 neighborhood. That cell's perception also depends on a per-cell orientation vector. Smooth manipulation of those orientations allows texture projection on an arbitrarily rotated vector field. In our first experiment, we trained a number of cell automata models to grow and persist various predefined patterns, trying to mimic the development and regeneration of a multicellular organism. In the next experiment, we used the VQGAN network-based texture synthesis loss. We trained cell automata that produce textures similar to the provided examples. The objective doesn't enforce pattern stability, so the proposed method happens to turn static images into living textures. We can also use feature channel activations of the pre-trained inception network as a guidance signal. Cell automata becomes yet another differentiable image parameterization for feature visualization. Feature channels reveal a plethora of interesting patterns and behaviors. Regular structures tend to produce particularly interesting behaviors, trying to establish global order from local interactions. In this experiment, we combine 2 different cell automata rules on the same grid. The boundary region executes a weighted combination of those 2 rules. We observe the capability of related CAs to produce a smooth transition regions, where patterns seeded by one rule continue into another. we call rules related if one of them is a fine-tuned version of another, or if they share a common ancestor. In the next experiment, we train the neural CA model for a missed digits classification. Only cells belonging to the digit participate in the computation, and the cells are only allowed to communicate with their immediate neighbors. Our training protocol ensures that cells reconsider their decision in an aligned fashion if the pattern gets altered. In the last experiment, we trained the model to mimic the... Well, this work was unfortunately not yet published. It's model trained by Peter Whedon, and well, he didn't publish it yet. But the objective function penalizes the per pixel difference between the CA-generated pattern and the rendering produced by the physical simulation. So the idea here is to have a cell automata that replicates the dynamics of a physical simulation. And later I'll show a few more examples of neural cell automata that's trained for tasks beyond text synthesis. But now let me proceed to our most recent publication that's also related to text synthesis. But here we limited our models even further. Instead of just allowing them to communicate with neighbors, we stripped off the directional sensitivity, and the communication is restricted to diffusion. So essentially each cell is represented by a vector, and those vectors diffuse different components, diffuse with different diffusion coefficients. So the only method of updating the state is a local like chemical reaction. I put reaction in quotes because that's actually just a small neural network that produces incremental updates for current vector of chemical concentrations, also in quotes. So concentrations can actually become negative, but we think this is a first step of something that can be in the direction of designing systems that can be really deployed as systems of chemical reactions. And the objective is the same. We design a system that should reproduce a pattern, but now, given the whole system is completely isotropic, we have to come up with a special loss that allows to, well, tries to matches current texture produced by the system with a bunch of rotated versions of the target sample. And also the system becomes really PDE. So now it doesn't all depend on the existence of this discrete cells. For example, I can slow down the diffusion in some regions of space to magnify patterns. So, slow down the reaction. So now diffusion acts faster and patterns grow larger. This can be interpreted as also using the irregular structured grid where nodes have different spacings, like different locations. And also we continued these experiments further. Here we apply our neural cell automata, those Stanford Bunny models, by just implementing the diffusion on the vertices along the edges. So each node is a vertex of the model. And what's even more like unexpected, given we trained models in 2D, and then by just running them at the volume, in 3D volume, for some patterns, we managed to produce a reasonable three-dimensional generalization. So like you train system in 2D, but then it can run on any manifold where diffusion operation is defined. So you can take two-dimensional system and run it in 3 dimensions. And sometimes it works. Sometimes it produces less coherent patterns. For example, this particular model, no, this one couldn't produce coherent stripes and developed into this unstable soup of like noise-like behavior. But for some, I think the structures are remarkably coherent with the two-dimensional versions of the pattern, and individual slices resemble the two-dimensional structures. And then a little preview of my what's next in neural cell automata. So this is the model of my most recent neural cell automata architecture running on ShaderToy, and you see there are two patterns. I use a special chroma extension to accelerate it, but there are two patterns, and those patterns are, each of those patterns is actually encoded with just 588 coefficients. So I made those models like 10 times more compact without losing much of quality, which, well, I'm doing this because one day I hope to eventually be able to reproduce them in real world, either systems of chemical reactions or as electronic circuits. And for this super compact system, I actually speculated a little bit about what could analog electronic circuit design look like. So these are, of course, like not a real circuit. Like this is just my demo where I tried to represent like registers that hold state of a cell as those bright huge quadratic nodes, like red hold negative value, green hold positive value, and then there is this matrix that maps the current states of cells and also states of neighbor cells into updates that feed back into those state holding registers. So one day I hope I'll be able to implement it as some sort of smart fabric. And also, well, what other things that can neural cell automata do? Here is a simple task that I threw at them, and they performed surprisingly well. Their objective, given a set of points on a plane, they must communicate with their immediate neighbors to build a minimum spanning tree. And well, there are some tasks that are surprisingly hard for them, but that one worked surprisingly well. Like not perfect, but I've got some very interesting behaviors. Like for example, here it makes two hypotheses and then one dominates, or even here where it first closes this loop and then another point connects to this and this edge gets removed. Of course, this may be not perfect, not the most optimal trees that are like possible with this set of point, but I was impressed to see this behavior. And I'm going to talk about those things in about a month in a live tutorial. So this is a little bit of a preview, and that's all I have. Thank you. And well, all the links I posted them in chat, so you can play with, for example, with these shaders and see what happens if you change individual parameters, how do they react. Okay, thank you.
Right.
I'm ready to answer questions.
Cool. Thank you, Alexander. I think we are kind of running behind time. So I'll ask one quick question, and then maybe folks can talk to you in the poster session. I think Mayur says, can't wait to experiment with this. I'm just curious, like you kind of showed a lot of stochastic textures. I'm wondering if, can you extend this to more structured patterns? I guess you have some structured patterns, but like, very structured scenes, do you see that kind of a limitation of this work?
Well, by structured patterns, do you mean grids? Something like
no,
this?
like natural images or something like that, like not textures.
Well, you mean, so there is this restriction of local communication that that determines the scale of the structures that this model reproduces. So it's like mostly works for textures, and well, during training, I unroll the cell automata to like maximum 100 something steps. So probably it's hard for it to pick up the dependencies. I'm considering adding some like the people were proposing hierarchical cell automata, like saying, okay, what if you have multiple scales? But I kind of not a big fan of this idea, because I'm trying to do things that are less structured. Like imagine, what if you have a chip, but your manufacturing process is designed that way that, contrary to how electronic designed now, that you can lay out like each route for each individual wire. Your manufacturing process is that you have well-defined local connectivity, and then you just scatter some global long-range connections on top of that. And if is there a way to design systems that can exploit those long-range connections in a useful way? So that's the direction I'm looking into for having like large structures or solving tasks that require global information.
Awesome. All right. Thank you so much again. So this concludes basically the talk part, the part of our workshop that has talks. We'll now have a poster session for the papers that are in this kind of second part of our workshop. We won't be returning back for a closing session. I think that's what it says on the website, but we won't be. But feel free to kind of join the poster session, talk to the authors of the poster paper.